Hello, my name is Connor Druin, and for the last in this mini series of presentations I'm doing, I wanted to discuss a paper called X-ray photoelectron spectroscopy of high-throughput mechanically exfoliated van der Waals materials. This paper is written by the names on the screen. I will not insult them by attempting to pronounce their names. So, the main principle of this paper was to use XPS or X-ray photoelectron spectroscopy to analyze the elemental composition of materials on uh, electronic devices that were exfoliated using a new technique that the team had developed. So, to begin, just sort of a primer on XPS itself. So, when a material is irradiated by an X ray beam, the energy of the X ray is absorbed by the electrons in the atoms, and if this energy is sufficient, then the electrons are ejected from the material, and this is known as the photoelectric effect. By measuring the kinetic energy of these emitted photoelectrons, the binding energy can be calculated using the top equation here. And since the binding energy is specific to an element in its chemical environment, XPS offers a fingerprint of sorts to identify both the element and sometimes even its oxidative state or bonding configuration. Um, Basic idea of how it works is a sample is cleaned and prepared, oftentimes under a ultra high vacuum condition to prevent contamination, um, followed by a monochromatic X-ray source. Irradiates the sample, and X-rays penetrate only a few nanometers, ensuring that the surface and near surface electrons are excited and ejected. These electrons are emitted from the sample and are collected by an electron energy analyzer, and then a spectrum is generated, displaying peaks at specific bonding energies, and each peak corresponds to electrons from a particular orbital of an element. So, what was the main point of the paper? So, the paper addressed the growing importance of van der Waals materials such as graphene or hexagonal boron nitride for next generation electronics, photonics, and energy devices. While traditionally mechanical exfoliation with the Scotch tape method has been used for producing high quality monolayers, its low throughput and limited practical application has prevented large scale production. To bridge this gap, the authors of the paper introduced the idea to mechanically exfoliate the van der Waals materials at high throughput and then use XPS as a non destructive means of characterizing the chemical surface. So you can see here, these are taken from the paper itself. Um, so the study describes a mechanical exfoliation designed for speed and scalability. Through these optimized procedures, large numbers of exfoliated flakes are generated, and this approach is intended to retain the quality of the materials while enabling a industrial scale up application. Um, these flakes are transferred onto common substrates, such as indium tin oxide (ITO) or silicon wafers with oxide layers that are compatible with further device fabrication. So XPS was performed under high vacuum using monochromatic aluminum potassium alpha source to excite the core electrons. The instrument was calibrated to resolve binding energy differences corresponding with various chemical states. The technique involved measuring kinetic energies of the photoelectrons emitted from the sample surface, and this produced a spectra wherein each peak corresponded to elements, specific oxidation states present in the materials. Particular attention was paid to the core electrons of the graphene used for the first analysis. The peak shapes, positions, intensities offered insight into chemical purity and bonding environment. You can see here the results of the graphene analysis. So the XPS spectra clearly confirmed that the expected elemental signatures of the van der Waals materials, for instance, in the case of graphene, The core level peaks, the MOD3, the SP2, and the C1S, appeared at binding energy consistent with unoxidized states, which indicated that the high throughput mechanical exfoliation did not produce significant chemical contamination. Um, One of the main concerns with exfoliation methods is the inadvertent oxidation or surface degradation of the material. However, the XPS analysis from this team revealed that there was no noticeable signs of oxidation or the formation of undesired chemical species. The XPS peaks also showed that the binding energies and the corresponding line shapes were in agreement with those of high quality or bulk or conventionally exfoliated counterparts. This implies that the electronic signature is maintained without adverse effects that might otherwise indicate alterations in bond or defect formation. The study also used the XPS to probe the chemical state of the atoms. For instance, the absence of extra peaks or shoulders in the metal or uh, chalcogen spectra provided evidence that the bonding environment was not disturbed by the exfoliation process. One significant finding was that the high throughput exfoliation method yielded consistently high quality surface results across multiple samples. The XPS measurements taken at different spots on the same flake or across several flakes showed very similar spectral profiles, and this reproducibility is critical for the practical application of industrial scaling. Speaking of, traditionally, mechanical exfoliation is effective but labor intensive with very low throughput. But by adapting this method for higher scale production, while still achieving the structural quality, this was established by the study that the mass production of these van der Waals materials for electronic applications was feasible. Although there was some degree of surface contamination, this is inevitable in ambient conditions. The XPS showed that these contaminants were minimal. The low intensity of these peaks reinforced the effectiveness of this new exfoliation technique. Um, and since surface contamination can adversely affect the properties when integrating 2D materials into these devices, the minimal contamination observed assures that the exfoliated films are well suited for further processing. So, looking to the future, you can see another material tested by the team. So the combination of high chemical purity preservation and the electronic structure, the reproducibility across large areas means that the mechanically exfoliated van der Waals materials are excellent candidates for next generation devices. These findings help bridge the gap between these small scale laboratory experiments and large scale industrial sized productions. The study also positions high throughput mechanical exfoliation comparative to CVD or chemical vapor disposition or any other bottoms up synthesis technique. While CVD offers large scale uniformity, it often requires stringent growth conditions. And in this case, the exfoliation method performed by the team was highlighted for its simplicity and its ability to be used without complex processing. So, strengths and weaknesses, as I see them for this paper. So, one strength of this paper would be the advancement of the so called Scotch tape method. This study introduced an optimized mechanical exfoliation method that aimed to increase yield while preserving the material quality. This is significant given that the traditional exfoliation methods are, as I said, often labor intensive and low throughput, and the possibility of scaling up the production of these high quality van der Waals materials um, moves towards their application in next generation electronics. Utilizing the X-ray photoelectron spectroscopy allowed the authors to non-destructively probe the chemical composition and electronic state of these exfoliated layers. And the analysis of the core level peaks provide convincing evidence that the exfoliation process does not produce any significant contamination. The study reports consistent spectral profiles across multiple samples and across different areas on the same flake, which is crucial for validating the feasibility of the method for practical use. and the work is positioned as an alternative to complex synthesis methods like CVD, um, which again the team emphasized the simplicity of this method. So, what are some of the weaknesses? Well, so although XPS information about the chemical composition was very robust, the study could have benefited from additional techniques such as Raman as a complementary method to provide more insight into like flake thickness and lateral dimensions, and possible defects that the XPS could not capture. Um, Another example would be the paper mentions reproducibility of XPS spectra, but would be stronger with a more in depth statistical analysis that quantifies the variation across multiple numbers of samples. While the high throughput exfoliation method was the main strength of this paper, it could have benefited from a deeper discussion on the actual trade offs of this method, rather than just discussing its throughput and uniformity. The study also primarily focuses on fresh mechanically exfoliated samples under controlled conditions. However, it does not mention how these materials might hold up over time at ambient conditions, whether degradation is a factor, how quickly these would degrade, and any potential damage induced during the manufacturing process of these materials. Um, and although the study promotes this high throughput mechanical exfoliation method, it doesn't explicitly compare it to any other state of the art techniques other than CVD. And providing these benchmarks relative to each other would go a long way to proving that the study truly showed the best process of producing these films. So, why XPS? Why use this technique over another? So, XPS excels at probing the top 5 to 10 nanometers of a material surface and providing detailed information about the elemental composition and oxidative states of that material. The level of the surface sensitivity is crucial for studying the mechanically exfoliated van der Waals materials, where other surface contamination could be a factor and affect performance. The ability to quantify not only the elements present but also their relative concentrations, chemical states, sets XPS apart from any other surface analysis technique. Also, the non-destructive nature, XPS is nearly entirely non-destructive, and this is important, especially when you're handling high-value 2D materials. However, that is not to say that other techniques could be complementary. These other techniques could not be used in solely, but they could be complementary. For example, ramen would provide excellent information on the crystal structure of these materials, as well as number of layers and any possible defects. However, it couldn't do this on its own. It would need to be a complementary method because it doesn't offer direct insights into chemical states or quantitative elemental composition. SEM EDS would provide high resolution images of surface morphology and a rough estimation of elemental composition, but it lacks the chemical state resolution and surface sensitivity that XPS provides. AES, or Auger electron spectroscopy, has high surface sensitivity and can be used for chemical state analysis. However, it's challenging in terms of quantification and often requires more complex interpretation. EELS, or electron energy loss spectroscopy, offers fine details on electronic structure and bonding. However, it requires access to a transmission electron microscope and very thin samples, two things that are not easily produced. So, while many of these materials can yield partial insights, none combines the depth of surface for the chemical analysis, the quantification, non destructive profiling that XPS provides. So while complementary methods can and often do help the understanding of these materials, XPS alone is responsible for this study, and replacing it without losing crucial information would not necessarily be possible. Anyway, so I've enjoyed discussing this paper. I suggest anyone who wants to learn more go read the paper itself. It's very interesting, and I've enjoyed this. Thank you.